Hello everyone, and welcome back to the AI Research Roundup. I'm your host, Alex. Today is May 4th, 2025. Alright, so we're diving into homomorphism expressivity of spectral invariant graph neural networks. This ICLR conference paper was published back on January 22nd, so just over 3 months ago now. Essentially, this paper explores how powerful graph neural networks become when they leverage graph spectra, like eigenvalues and projections, compared to standard message passing, using homomorphism counts to measure it. Okay, so to illustrate a key concept, let's look at this figure. On the left, we see what's called a parallel edge, basically multiple paths between nodes U and verses. Then on the right, you see a parallel tree built using these parallel edges, alongside its underlying simple tree structure. These parallel trees are crucial. They're exactly the kind of structures that spectral invariant GNNs can count homomorphisms for, which defines their expressive power. Alright, building on that idea of expressivity limits, let's look at this next figure. It shows a simple graph with 6 nodes, arranged in a sort of triangle pattern. This is presented as a counterexample. It demonstrates that while spectral GNNs are powerful, they aren't as powerful as the 2FWL test. This specific graph structure is something that 2FWL can handle, but spectral invariant GNNs cannot, placing them definitively below 2FWL in the expressivity hierarchy. Okay, so following on from that hierarchy, this figure shows 2 more important counterexamples. On the right, we see these diamond-like structures chained together. This structure is used to show that increasing the GNN's depth, or number of iterations, strictly improves its power. You actually need more iterations to distinguish longer chains like this. The left example? Well, that relates to comparisons with subgraph GNNs and local 2 GNNs. So this figure really brings together those comparisons we've been hinting at. It lays out the expressive power hierarchy, mapping out where spectral GNNs fit. You can see how just using eigenvalues is a starting point, then adding spectral invariance with 1 iteration is stronger, but still weaker than subgraph GNNs. Add more iterations, and spectral GNNs become incomparable to subgraph GNNs, but they always remain strictly less powerful than local 2 GNNs and the 2FWL test. Okay, moving to the results. This table provides some experimental validation for that hierarchy. We see different models compared: standard MPNNs, the spectral invariant GNNs we've been discussing, subgraph GNNs, and local 2 GNNs. They're tested on homomorphism, counting for complex patterns, the zinc molecular benchmark, and counting simpler substructures. Well, the numbers generally back up the theory. Spectral GNNs beat MPNNs, but often lag behind subgraph and local 2 GNNs on these counting tasks. Okay, and underpinning those results and the theoretical hierarchy, this is actually the table of contents from the appendix. It shows exactly where the detailed proofs for the key theorems reside, like for theorem 3.3, which formally connects spectral GNNs to counting those parallel trees we mentioned. It also points to the experimental setup details and further analysis, essentially providing the rigorous foundation for the findings we've walked through. Right, and speaking of specific theorems mentioned in the appendix, this figure shows 2 graphs, G and H. These are presented as counterexamples related to theorem 3.10. Now, that theorem concerns what graph properties can be distinguished using only eigenvalues. So, these particular graphs likely demonstrate limitations, structures that eigenvalues alone cannot tell apart, really highlighting why the projection matrices used by full spectral GNNs are crucial for boosting expressive power beyond simple spectral counts. Alright, so to bring it all together, the homomorphism expressivity framework gives a really precise handle on spectral invariant GNNs. It clearly maps out their power, showing they beat standard message passing but can't reach 2FWL, and that projections and depth are key for distinguishing graph structures. Well, that's our roundup for today. Thanks for joining me. I'm Alex, and I'll see you next time.